All right, we're back. We're still on page 9 of notes 2 of Calc C, and we are going to keep doing the problems. So if you got this far, hopefully you know what we're doing. We're trying to write a Taylor polynomial, approximate a thing, find an error, state a range, see if we got it right. That's like our goal. So let's see if we can do that. So write the Taylor polynomial, centered at x equals 0, having 4 non-zero terms. I'm going to show you a weird way to do this. It's actually the way that you're always going to do it. If you already memorized the series for the polynomial, it's going to be a series. It's going to have an infinite number of terms. If you already memorized the pattern for the polynomials for e to the x, you can kind of write them down. I'm going to say e to the u. Whoa, auto shapes. Get out. Uh-oh. We're crashing. How crashed are we? What do I got going on here? Got some stocks. All right, let's see. Back in. Okay, so e to the u. E to the u is 1 plus u squared over 2 factorial plus u cubed over 3 factorial. So you might not know this yet. And also this is an approximation because it goes on forever. So I'm going to say it's approximately. So then e to the 2x is approximately 1 plus every u becomes a 2x. So it'll be 2x, and then I'm going to say 2 squared x squared over 2 factorial plus 2 cubed x cubed over 3 factorial. And then if you want, you could, so the calculator is definitely going to, so I'm going to say this is p of x, which is actually equal to 1 plus 2x. This is what the calculator is going to give, because it, well, actually, I'm still not going to simplify. This is not what the calculator will give, because the calculator is going to simplify these factorials, but I'm not going to, because humans don't do that. Okay, so we get this. Now I'm just going to use calculator anyway, but I thought it was important to do this, right? So let's see. We have, so I'm going to start a new document, 16. F of x is e to the 2x, and then, so I need the Taylor polynomial. So I'm going to type Taylor. You can do menu 4C1, menu 4C1. Try that. F of x is my function x. I need 4 non-zero terms, but really I just need to go to the third degree here. Usually I just play around with this and make sure I get what I want, and I'm centering it at 0, so I don't need to put an argument. So the calculator simplified it. Let's store that as p of x. And then, all right, so I'm supposed to approximate e to the 0.6. To get e to the 0.6, I'd have to plug 0.3 into the function. So I want to do p of 0.3. And I get 1.816, which is like a weird jumble of the golden ratio, sort of. So p of 0.3 is approximately 1.816. All right. So now, determine the maximum possible error. All right, to get to the third degree polynomial, I need to use up to the third derivative, which means to find the error, I have to go to the fourth derivative. It's going to be the maximum of the n plus first derivative. It's the maximum of the absolute value of the n plus first derivative. I keep forgetting that because the derivatives keep being positive. So maximum of the n plus first derivative. So I need to find the fourth derivative. Because I used 3 derivatives to get my polynomial, I need the fourth derivative here of f of x. So 16 e to the 2x. So I'm going to go back to the notes so I can write this in so that it's clear what's happening here. Because there's like a lot going on. I find people stress out about this, and it's like just not as bad as it should be. So let me, maybe if I make a note here and say p of x used up to f triple prime of x, right? So therefore, m uses the fourth derivative. So it's all about like, what did you have to use to get your polynomial? Once you know that, you can kind of like do the problem. So we are looking for the maximum of on the interval from 0 to 0.3, because we're approximating the function at 0.3 and it's centered at 0. So 0 to 0.3, the absolute value of the fourth derivative, which is equal to the maximum on 0 to 0.3 of the absolute value of, I think it was 16. I'm not going to switch. I'm just going to look. 16 e to the 2x. 16 e to the 2x. Okay, now this, so the actual value of this is definitely 16 e to the 2x is an increasing function. It's definitely 16 e to the 0.6. Like that's definitely what m should be. So what I'm going to do is I'm going to say that this is definitely less than or equal to 16. E is less than or equal to 3, so I'll use 3 there. And then 0.6 is less than 1, so I'm going to use this. So I'm going to use 48. But that's just m. So m is going to be 48. The actual error, I'm going to say that I'm going to say the absolute value of the error is less than or equal to m, right? So 48 times, then absolute value, I'll switch color, the absolute value of 0.3, which is what we're plugging in, minus 0, which is the center, to the 4th power over 4 factorial. And then this is equal to, I don't know, 48, and then times 0.3 to the 4th over 4 factorial. This definitely simplifies, but that's okay. I don't really need to do that. I'm going to name that E, capital E, equals capital E. So my range of values, and we'll jump to the calculator in a second, my range of values should be my approximation, so P of 0.3 minus E that I calculate, less than or equal to F of 0.3, less than or equal to P of 0.3 plus E. And now it's all calculator from here on out. So let's go back and let's get the calculator to, we'll store our value for the error. So I'm going to say error is 48 times 0.3 to the 4th over 4 factorial. Okay, but it's like pretty small. And then if I do P of 0.3 minus the error, I do P of 0.3 plus, you should actually just paste this down. This really small interval here. So that's 1.7. I'm going to go 4 decimals so that I don't just round this thing to 1.8, I guess. Yeah, I'm definitely doing that. 0.7998 less than or equal to F of 0.3 less than or equal to 1.83. When I like first learned this stuff, I had no appreciation for what we're doing right now. Like it's very cool. Like we're putting a bound. Like we can. So if you have a polynomial, you can plug anything into it because it's just a matter of like effort to evaluate a polynomial, basically. So like you can plug 0.3 into a polynomial, not a problem. When you plug 0.3 into this polynomial, it gives you an approximation of e to the 0.6. And if you ask me to approximate e to the 0.6 without this idea, no clue. I have no clue at all. But now I know that it's somewhere between like 1.8 and 1.83, basically. So let's see if, let's see what f of 0.3 is. So there you go. It's between 1.8 and 1.83. Like that's insane that you can do this. Approximations are very cool. So we definitely got it right. You can like ask the calculator, did we get it right? But it's just, if it doesn't say true here, you definitely did something wrong. But it did work. So let me just write down that e to the 0.6. Is that what we're doing really? E to the 0.6 is approximately 1.8221. And it worked. So let me go back to the notes so you can take a look. Then we will end the video because I think we conquered this problem. So let's see. The only other thing that we could be doing that I think would enhance this a little bit is graphing. Graph f of x and graph your polynomial. Go back and try that and you'll see like they're really similar on the intervals that we're looking at, which is why we're getting such good approximations, but it worked. It's gonna be really disappointing when I make one of these and it doesn't work. It worked. There you go. All right, so I'm going to end this here, come back in the next one, and do a little bit more. So I will see you there.